So let's bring two concepts together. Random errors, type A, and systematic errors. The main difference is that type B, systematic errors, stay the same, no matter how many times you repeat your measurements. Type A, random error, will dramatically drop down with increase of number of measurements. That happens by two means. First, most important, we have division by square root of number of measurements. Second, student's coefficient drops down as well, which means we have better estimate of our standard deviation when we do more measurements. As you can see from this plot, random error at small numbers is dominating total uncertainty. With increase of number of points, somewhere here, effect of random and systematic error becomes practically equal, and with further increase of points you have no improvement of your results, because systematic error will dominate the picture. So perhaps this will be the right place to stop data collection, because you are not making things any better, you are just wasting time and money. Let's do example. I titrate unknown solution using class A 50 ml burette. My results show standard deviation of 0.05 milliliters. How many measurements I need in order to get confidence interval of plus minus 0.04 ml? Okay, looks relatively easy because I'm hooking the numbers in a formula, and it's visible that for two measurements confidence interval is very large, plus minus 0.44. With four measurements it's much smaller, and at 9 measurements is becoming smaller than 0.04 mils. We can continue further, and confidence interval is becoming even smaller. But does it make any practical sense? I am using class A burette, which means that the burette has tolerance of 0.05 mils. Now total uncertainty is coming from this uncertainty of burette and my statistical uncertainty here. If I'll take this into account, I'll have different numbers. For the first number, the difference is invisible. Statistical error dominates the picture. But further, 0.05 is becoming close to my confidence interval here. So for 9 measurements, I do not have 38, I have 0.06. And then slowly, my numbers are coming closer to 0.05, the uncertainty of my burette. I never have uncertainty of 0.04, no matter how long I'll be titrating. It's a good idea to stop somewhere at reasonable number and never go, say, beyond 8 or 9 in this particular example. So, which one I'm using? systematic or random, or two? Answer is, we are using that one which gives larger uncertainty value. So one more example. I'm running acid determination in a sample using again 50 ml class A burette. Analytical balance is to weigh my samples of 0.4, 0.5 gram size and 0.1 molar sodium hydroxide premade solution I bought, so-called Fixanal, that is certified to have relative error of 0.2% or 0.02. Now my results determination are 40.00, 40.10, 40.15 and 40.20%. So what is uncertainty of this data? First, average or mean is easy to calculate and it's 40.11%. Now I want to estimate error coming from type B. Errors of weighing, so tolerance of my balances divided by weight of my sample, will give me a very small number. A burette will give much more visible number. I am assuming that I am properly titrating using volumes between 30 and 50 mL with 40 average. And then the largest relative error is coming from my Fixanal. So this number will dominate the picture and will give me uncertainty of 0.08%. That's my estimate for my type B error. Type errors are easy to calculate using student's coefficient, standard deviation from these numbers, and square root of n, which will be 4. And it is 0.14%. This number is larger than this number, so I can say that the answer will be 40.11 plus minus 14%. Well, if I'll do very precise calculations and I'm very confident, I can take into account all these numbers and the uncertainty will be slightly larger and perhaps it will be more realistic. So say 0.15 would be better choice. Now the next example. Exactly the same determination, so everything is the same, but first number is not 40.00 but 40.15. Everything else is exactly the same. Mean value or average is slightly larger, 40.15. Type B errors are exactly the same, we didn't change anything. But type A errors in this particular case are much smaller, 0.06%. They are smaller than type B errors. I cannot use this number as my uncertainty estimate. I need to put type B estimate instead, which is larger number. If I am very picky, I should do more accurate calculations, taking these and these numbers together, and I'll have even larger uncertainty, which would be perhaps a good idea. Again, which one we are using depends. If your type A is very small, you may need to use type B. Practically, in most cases, in students' lab, type A errors will dominate. So you'll never use type B calculations. Now, how can we use confidence interval for two different numbers? They are very complex statistical methods. You can read them in your book, or much better, use textbooks in mathematical statistics. Now, for purposes of our class, we'll be using very simple rule. If confidence intervals overlap, you cannot see the difference. From point of view of your measurements, this is the same. So, for example, green and purple intervals overlap, so you do not see the difference. 23.8 plus minus 0.9 and 24.5 plus minus 0.9. These two intervals overlap, so you do not see statistical difference between these two numbers. Now, if confident intervals do not overlap, that means that these two numbers are different. 23.8 plus minus 0.2 and 24.5 plus minus 0.2 are different numbers because these intervals do not overlap. Now, the numbers actually are the same, but confidence intervals are more narrow. It's very important to remember not to underestimate your error. Many people want to look good, so they are placing smaller and smaller errors. Sometimes not even cheating, just conveniently forgetting some sources of uncertainty. This can be negative. For example, you were given unknown certified standard, and it appears that your data disagree with well-known value. Now, if you have exactly the same numbers, but you assume that uncertainty is larger, there is agreement between two. Now, if your uncertainty was underestimated in this case, you made a mistake and you are getting wrong conclusions.